What's up, math scholars? Mrs. Harp here for another 2.7 day 3 video. It's René Descartes' rule. This guy was a famous mathematician that lived in the late 1500s, early 1600s in France. It's a sunny day where I am. I hope it's a sunny day where you are. Who's excited to learn some math? Woo! 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 I have an empty classroom. So, René Descartes' rule of signs is basically a way for you to discover what type of possible solutions a polynomial will have. You can find the possible positive solutions by counting the sign changes in the polynomial from left to right. So simply count the sign changes, and it will be that number or less than that number by a multiple of 2. So for example, if I count the sign changes, I can get 5. My possible zeros would be 5 or 3 or 1, because I'm subtracting off 2 repeatedly till I run out of numbers. For possible negative zeros, you find f of negative x. Then you count your sign changes. And it's that number or less than that number by a multiple of 2. For possible imaginary zeros, you're going to look at the degree of the polynomial, and it's going to be an even number, smaller than that or equal to that. And it will definitely depend on what your scenario is and what would work. So we're going to have to always keep our mind on the fact that the degree of the polynomial is the amount of solutions there are, and just look at our possibilities. So what I'm going to write down for this is look at the degree, and then consider all even numbers equal to or smaller than that. The reason it has to be an even number is imaginaries come in pairs. So you could have 2 imaginaries, you could have 4 imaginaries, you could have 6 imaginaries, but you could never have 3, because you could never have an odd amount of imaginaries. Maybe I'll jot that down. Imaginaries come in pairs. So in 0, you could always have 0 imaginaries. That would be a possibility. So 0 is counting as an even number in this case. Didn't need to erase that much. Okay. All right, so let's try our first example problem. This is my polynomial here. Look at it right away, and I realize that my degree is 5. So I will have 5 total solutions. Some will be positive, some will be negative, and some might be imaginary, but there'll be 5 total solutions. Here's how we count sign changes. We start by looking at the positive 4. When it turns to a negative 3, that counts as 1 sign change. Then it stays negative, negative 6. That does not count as a sign change. Then it goes to positive, positive 8. So we have 2 sign changes because we went from positive to negative and back to positive. So for possible positives, we go 2 or 0. For negatives, that's going to be the one that requires some work. Since we're finding f of negative x, you basically put a negative x in everywhere you see an x. But then you have to simplify it down, and you really have to think about how the exponents will affect negative numbers. For example, right here, I start with my exponents because of order of operations. If I would take a negative x to the 5th power, it would make that term negative, so the whole entire term will turn to a negative 4x to the 5th. If I go to this term right here, my negative x to the 3rd power will be negative, And a negative with a -3 will turn that whole term positive. Finally, my -6 and my -x will turn to a +6, and then I have a +8. So when I go to count my sign changes, I'm starting with a -4x to the 5th, turning to a +3x to the 3rd, and staying positive the rest of the time. So for possible negative solutions, I only have one. Now I'm moving on to imaginary. The degree is 5. So my possible imaginaries right off the bat would be 4 or 2 or 0, all the even numbers less than 5. But what I really have to do is think, would all those actually work? Could I get all these different combinations of solutions to add up to a total of 5 solutions? Because my degree was 5. So there's 5 total solutions, and I need to think, would the combinations help me with that? So let's think. If I had 2 positives and 1 negative, that'd be 3. I would need 2 imaginaries. So that would work out. That would give me 5. If I had 0 positives and 1 negative, that'd be 1. Then I would have 4 imaginaries. So what I think we're figuring out here is we would never, ever, ever have 0 imaginaries. So I'm going to cross that off, because if I had 0 imaginaries, I would need all 5 solutions to be positive and negative, and that's not going to happen here. So that's what kind of how you do your imaginaries. You look at the other possibilities, the possible positives, possible negatives, and see which of the imaginaries would help you add up to 5 total solutions. Let's try our next one. For possible positives, I'm going to simply count my sign changes. My imaginaries go. Oh, here they are. Oh, okay. To count my sign changes, it looks like I'm going from positive x cubed to positive 2x to negative 11. That's only one sign change. So one possible positive solution. For possible negatives, I'll put a negative in everywhere I see an x. And simplify that down. A negative to the 3rd power would be a negative term. 2 times a negative x would be a negative 2x, and then I have negative 11. Now, if I'm counting sign changes, I'm not seeing a single sign change. It's going from negative to negative to negative. So there's 0 possible negatives. For my imaginaries, I look at the degree, 3, and I go with every even number smaller than that. But now I have to think, would both of those actually work? I'm going to have 3 total solutions for the problem. It's degree 3. Let's see what possibilities would work. If I had 1 positive and 0 negatives, I would need to have 2 imaginaries, and no imaginaries would never even work. So get rid of the possibility of having 0 imaginaries. That is number 9. Number 10. My imaginary again, just kind of hiding, I betcha. Ooh, it's off the picture. We'll just have to do a little scrolling. For possible positives, when I count my sign change, I'm going from positive 2x to the 4th to negative 8x, that's 1. Back to positive 6x squared, that's 2. Back to negative 3x, that's 3. And back to a positive 1, that's 4. So we're with 4 or 2 or 0. For my negatives, here it goes. I'm going to put a negative x in everywhere I see an x. Ooh, that's a lot to simplify down. My first term will be positive because any even number, any negative number to an even exponent would turn positive. My next term would actually be positive as well because it's a negative 3rd power, which is negative, but partnered with a negative 8 would turn positive. It'd be a double negative. My next term would be positive because it's negative x squared, so that'd turn positive. My next term would be positive too because it's a negative 3 with a negative x. And then I have my final positive 1, obviously. So it looks like there's 0 sign changes here. Every single term is positive, so it's 0. And finally, my imaginaries, it's down off the screen, so I'll just write imaginaries right here. Imaginaries, the degree is 4. So we're going to go 4 or 2 or 0. But then think about if that would work. So since my degree is 4 in this polynomial, I'm going to have 4 total solutions. Let's see what combinations work. If I have 4 here and 0 here, then I would have 0 imaginaries. If I have 2 here and 0 here, that would mean I would need 2 imaginaries. And then if I had 0 here and 0 here, I would need all 4 imaginaries. So I think we're good. All my different combinations of imaginaries would work to give me that total of 4 solutions. And we have one more thing to show you guys, and it is in the calculator. Some classes already know this trick because I showed it to them earlier on in maybe the end of chapter 1, but some classes have never seen this trick. There's a way to use your calculator to find the x-intercepts or the solutions of a polynomial. It's in the calculate menu, second trace. So I'll show you how this is done. I'm going to type the equation into my calculator. X to the 5th, 2x to the 4th, minus 8x to the 3rd, plus 4x squared, minus x minus 1. So the degree of this polynomial is 5. There's 5 solutions, but visually, I'm only seeing 3 of them. What that means is 2 more are imaginary that we're not seeing. So to find them in the calculator, it might actually benefit us to zoom in once. Let's see what that looks like. Zoom to enter will zoom you in. I mean, I kind of like that I can see them closer, but I'm actually going to rewind and I don't actually want to zoom in. So zoom 6 real quick. All right, so here's the process. Every time you want to find a solution, you have to start this process back at the beginning. You do second, trace, number 2. And then they start asking you a series of questions. They'll ask you left bound, question mark, right bound, question mark, and guess, question mark. So you have to decide what solution you want to find. I want to find the one with the green dot right here. My board's a little bit misaligned, but I basically want the solution to the furthest to the left. So I'm going to pick a number left of that solution I want to find. How about -4? I type the number in and click enter. And what that does is it creates a left boundary for my search zone. I'm creating a search zone so the calculator can search between the arrows for a solution. So my right bound I'm going to create is -1, enter. Now see those arrows at the top? They're pointing into the search zone. For guess, you don't need to make a guess. You can just hit enter. And it'll find the first solution for you. -2.2. There's 2 more solutions, so I'm going to use that process 2 more times. Second, trace, 2. A good left bound for my next answer would be -1, and a good right bound would be 0. So my calculator is now searching between -1 and 0 for my second solution. Enter for guess. It's -0.3. And one last time for the third solution. Second, calc 2. I'm going to make my left bound a 0 and my right bound a 2 because it kind of looks to me it's between 0 and 2. And there you go. Now, what's cool about these bounds is you don't have to use the same bound as I'm using. You don't have to use the same bound as your neighbor is using. You just need to find a search zone that will tell the calculator where to search to be able to find a solution. So thanks for watching today. This was 2.7, day 3. Bye.